Welcome to the fourth video lecture in Discrete Mathematics. In this lecture, we will continue with our study of propositional logic and predicate logic. To recap, we have seen that in propositional logic and predicate logic, every statement is either true or false. A statement can be formed of other statements connected to each other using 5 different kinds of connectives: and, or, not, imply, and if and only if. We also saw that a statement can have variables, unspecified terms, but all the variables has to be properly quantified using the two quantifiers for all and there exist. We also saw that any meaningful statement or proposition or theorem can be written as a mathematical logic statement. A statement is called consistent if for any setting of its variables, which means smaller statements, to true or false, the statement always evaluates to true. So this gives us a way of checking whether a theorem or a statement is logical or not. Now, there can be multiple different ways in writing a particular statement. Or in other words, there can be multiple different mathematical logic statements which basically mean the same thing. So these statements we call as equivalent statements. So we say that two statements are equivalent if their truth tables are same. For example, consider this statement: A implies B. I claim that this statement A implies B is same as saying not B and A is false. So how do we check them? So of course the way of checking them is via their truth table. So for example here, I have written the truth table. So for all the possible inputs of A and B, that means A can be either false or true, similarly B can be either false or true, we would like to write the truth table or the what is evaluation of A implies B and not B and A equals to F. So let's do it one by one. If you remember the rules of implies, a false statement always implies a false statement, or a false statement implies a true statement. Both of them are true. So if A is false and B is false, false implies false, yes, it is true. False implies true, yes, it is true. A true statement, whereas, implies only a true statement. A true statement cannot imply a false statement. So true implies false is false, and true implies true is true. Now let's look at the truth table of not B and A. Now let's see. Let's try to do it quickly. If B is false, not B is true. So in that case, if A is false, true and false is false. Yes. If you remember that for the case of AND, only time it is true is only when both of them are true. So this is in fact false when A is false and B is false. So it is true. Similarly, when A is false and B is true, again false and anything is false, so it is false. So this statement is true. Now if A is true and B is false, then what happens? Then not B is true, true and true is true, so true cannot be equal to false, so this sentence is false, so this is false. And again, if A is true and B is true, then not B is false. Then not B and true is false. So this is again true. Thus, we see that the truth table of both the statements are same, which means that they are equivalent. And here is the truth table of them. Now, I have listed a number of problems which will be very important in the coming up lectures. So, prove that A implies B is same as not A or B. Prove that A, if and only if B, implies A implies B and B implies A. Prove that P or Q implies R is equivalent to P implies R and Q implies R. Similarly, prove that A implies B is equivalent to not B implies not A. So I leave you guys with these problems. I will use these problems, the statement of these problems in the coming videos. Very crucial. Now, let's go back to the definition of equivalence. As I told you, checking equivalence is same as checking if the truth tables are same. As you can imagine, when these mathematical logic statements are big, or in other words, when there are quite a number of variables, in that case, doing the truth table can be quite a tedious process. There is one more way of checking equivalence. Namely, instead of using brute force truth table approach, we can simplify the formulas using some rules. So here are some of the useful rules. Again, you can check it for yourself that all these rules are correct. That means these rules can be proved from the truth table. To remember these rules, let me give you a small tip. These rules are identically same as the rules for set operations. Namely, if you can replace AND with intersection or with union and not with complement, you get the same set of rules as you saw in the case of set operations. So, remembering these rules is not a hard job. Other than this set of rules, there are a couple of rules that are for the quantifiers, particularly the negation of quantifiers. Namely, if the proposition is of the form for all x px, where px is the proposition using the variable x and it is quantified using for all x, then the negation of this is, or the opposite of this statement for all x px is, there exists an x such that px doesn't hold. Or in other words, for there exists an x such that negation of px is true. Similarly, the negation of there exists x px, meaning there exists x such that px holds or px is true. The negation of this is for all x, px does not hold. This set of rule is very useful for various purposes. We will see some of them right now. Now, here is a problem. This problem is saying that let's take P or R or Q and not of P and not of Q and not of R. This particular expression is equivalent to which of the following? Let's try to solve this problem. We will use the rules of propositional logic that has been listed out here. To start with, let's use the De Morgan's law, which says that not of P or Q is same as not of P and not of Q. So let's see how can we use that particular law. Let's apply the De Morgan's law in this particular term. So that means not Q and not R will become not of Q or R. So this term, whole term, is congruent to P or R or Q and not of P and not of Q or R. Now I can apply De Morgan's law again in this term, and I will take the negation inside and I will get the first term remains same, P or R or Q, and so I will get not of P or not of Q or R. So not is negation of negation is the same thing. So this is nothing but Q or R. Now I can use the commutative law to replace this Q or R to R or Q. So let's do that. Let me just remove this, and this can be written as R or Q. Now I can apply the distributive law, which means that I can take away R or Q away and I get P and not P or R or Q. Now what is P or not P? P and not P. Note that when P is true, not P is false. And in that case, I get true and false is false. Similarly, when P is false, not P is true. So, this again becomes false and true is false. So, this term is always false. So, I have false or R or Q. Now, a false or anything is same as that object. A false or true is true and false is false. So this is nothing but R or Q. Thus, okay, and R or Q is nothing but Q or R by the commutative law. So that means this one is congruent to Q or R. I applied the distributive law, the associative law and the De Morgan's law multiple times to check that the given equation is equivalent to Q or R. Okay, now moving on, let's try to see if we know how to apply the rules of negation. So here is a sentence. There is a university in USA where every department has at least 20 faculty and at least one Nobel laureate. So what would be the negation of this? So out of these four choices, which one is the correct negation? Now, if you want to negate this sentence, first thing to do is to identify the quantifiers and the variables. So in this case, there are two quantifiers and two variables. There is, so this is a quantifier, there exists, with the variable university. Let's call this university as X. A university in USA, that's X. And then there is another quantifier, namely every, that is for all. And the variable here is department, let's call this one Y. So the equation is of the form, there exists X for all Y. Now there are two propositions. What are the propositions? Have at least 20 faculty. So let me call this one as P. So P and, so I have to write an and, at least one Nobel laureate, which is, let me call this one, at least one Nobel laureate has the condition Q, so Q. So this is the equation that we have. There exists X for all Y, P and Q. Now if I want to negate this term, what do I get? We first apply the rule of negation. Namely, this one becomes, therefore the first one, there exists X. Note that not of there exists X means there for all X, negation of the whole thing inside. So for all Y, P and Q. Once again, let us apply the rule of negation. So there not of for all Y is same as, so the first outer term remains the same, not of for all Y becomes there exists Y, not of P and Q. And now once we have not of P and Q, we can apply the De Morgan's law and we can see that this becomes for all X, there exists Y, not of P or not of, sorry, I ran out of space, not of P or not of Q. So if I have to negate it, it should be for all university in USA, there exists a department such that opposite of at least 20, meaning either it has less than 20 faculty or it does not have a Nobel laureate. So the right answer is the C, that means for all universities in USA, there is a department that has less than 20 faculty or at most one Nobel laureate. Now using the same trick or same method, any sentence can be negated. First convert it to a mathematical logic statement and negate it. The chance of making a mistake is minimal if you follow this particular procedure. If you have any doubts about how to negate a sentence, be it the English sentence or math sentence, find out the quantifiers, find out the variable, find out the propositions, and negate it using the set of rules. So this brings us to the end of propositional logic and predicate logic, at least the basic rules of that. To recollect again, every statement is either true or false. There are logical connectives and or not, implied and if and only if. We say that two logical statements are equivalent if the statements are identical for all input. To check the equivalence of two statements, we would either check by writing the truth table of both of them or by reducing one to the other using a set of rules, the rules that we have just discussed. There are two important symbols, which are the quantifiers for all and there exist. Some statements can be defined using a variable. For example, we can say something like, for all x in z, 4x squared plus 3 is divisible by 5. Or, there exists x in z, 3x squared, 4x squared plus 3 is divisible by 5. Now, these two are examples of propositions which has variables, namely x in them, and they are quantified properly. In the first one with for all x, the other one has there exists x. Now that we have set up the propositional logic, the predicate logic, and how to check equivalence, we can use this framework to design mathematically correct proofs. So how do I design that? So again, a mathematical sense statement comprises of a premise and a deduction, like all other mathematical sentences for the theorem. So a mathematical statement can be read like, if A is a set of assumptions and B is the deduction, it is of the form A implies B. Now, if A implies B, this sentence you have already seen in the exercises that I have given to you in the beginning of this particular video, that A implies B is equivalent to various other forms or various other ways of writing it out. So depending upon whether A can be written as union, and of two more statements or all of two more statements, or B can be written as and or all of statements, we can come up with different proof techniques. Now to check whether the statement is correct or not, we need to give a formal proof. Namely, if A implies B is indeed true, then we have to prove that. And as I told you, depending on whether A and or B or both can be split into smaller statements, we can come up with different proof techniques for solving A implies B. If indeed we can somehow prove A implies B, then we can call it a theorem. Next week, we will go into different proof techniques. I would request you guys to go and do the exercises that I told you in the beginning of this video, where I have asked you to prove various equivalences between the statement A implies B and other forms. It would help us to set up the different proof techniques. Depending on the problem, sometimes some proof techniques will be more useful than the other. We will be going through the different proof techniques one by one. Just to give you a highlight of what's going to come, there are a number of proof techniques. Namely, there are these constructive proofs. proof by contradiction, proof by contrapositiveness, induction, counterexample, and existential proof. We will try to spend a lot of time doing various proofs or solving various problems using different all the proof techniques. We will describe the proof techniques and see under what circumstances which proof technique works better. This will be basically our plan for the next 2 or 3 weeks. Thank you.